Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Find the minimum area to cover all ones too. Though the number of accepted solution is less during the contest, if you solve it step by step, this problem is not that difficult. When I say step by step, I mean the problem asks you to find out 3 non-overlapping rectangles that will cover all the ones. Instead of starting with 3 non-overlapping rectangles, try to solve the exact same problem for 1 non-overlapping rectangles. And then maybe find out whether you can figure out 2 non-overlapping rectangles with minimum area that can cover all the ones. And then head to finding out 3 non-overlapping rectangles that will cover all the ones. So that's the exact thing you should follow while solving a hard problem during the contest. If you are not able to tackle the original problem itself, try to solve a simpler version first and then build up on that to solve the original problem. So if you haven't gone through that thought process yet and you want to give it a try, you can pause and come back after you have thought about it. So let's get started. The problem states that you are given a 2D binary array grid. You need to find 3 non-overlapping rectangles having non-zero areas such that it will cover all the ones given in the rectangle. You return the minimum possible sum of areas of these 3 rectangles. Note that the rectangles cannot overlap, but they are allowed to touch each other, right? So let's take an example. Let's say the grid is 1 0 1 1 1 1. Now here all the 3 rectangles that are chosen is colored with 3 different colors, and the sum of areas of the chosen rectangle would be 2 plus 1 plus 2, which is 5. And because you haven't covered any of the zeros in any of these 3 rectangles, that's the best solution you can have, because that's the minimum possible area if you want to cover all the ones, right? So 5 is the minimum possible area here. Let's take one more example. Let's say the grid is 1 0 1 0 0 1 0 0 0 1. So again, the 3 chosen rectangle are colored with 3 different colors. Notice that in this time we have 0 in rectangle as well. The current area is 3 plus 1 plus 1, which is 5. You can try out any other possible configuration of 3 non-overlapping rectangles. You will not be able to cover all the ones in less than an area of 5, and hence the answer here is 5, right? So hope the problem statement is clear. Now let's try to solve a simpler version first. We will try to solve the exact same problem with just one non-overlapping rectangle. That means given a rectangle or given a grid with zeros and ones, figure out what is the minimum area of a rectangle you can put here which will cover all the ones in the grid, right? So what is the brute force way to approach this? Brute force way would be try out every possible rectangle, count the number of ones in those rectangles. If the number of 1 in the current rectangle is equals to the number of 1 in the original rectangle, the current rectangle you have chosen is a valid candidate, and among all possible valid candidates, select the one with the minimum area. So let's just look at it. So let's say you try this possible rectangle. This is one possible rectangle, and number of ones in this rectangle is 5, whereas the number of ones in the complete rectangle is 7. So 5 is not equals to 7, so this rectangle is not a valid candidate, right? Similarly, you can take out, like, this is one of the possible rectangle as well. Number of 1 in this rectangle is 7, number of 1 in the original rectangle is also 7. 7 is equal to 7, so this is one possible candidate for the answer. In other words, 1 2 3 4 5, so 15, we have found a rectangle with area 15 that will cover all the ones. So we will keep on trying all possible rectangles. Among all possible rectangles, we will pick the one which are valid, and among all the valid ones, we will pick the one with the minimum area, right? So what is the overall time complexity of this algorithm? We are iterating over all possible rectangles, right? Now, how to iterate over all possible rectangles? The rectangle is found by 2 points, top left and bottom right. If you know these 2 points, you can form a rectangle, right? So how many different top left point are there, multiplied by how many different bottom right point are there, and you can get the total number of rectangles you can have for this grid. And for all of these rectangles, you will figure out the sum of ones and do figure out the one which is valid and has the minimum area. So the overall complexity is order n cross m multiplied by n cross m. Why? Because number of different values of top left cell would be n cross m. Number of distinct values of bottom right cell would also be n cross m. So this is the total number of rectangles you can have. Now for each rectangle, you have to figure out the sum as well. Finding out the sum of a sub-rectangle, you can do easily with the prefix sum. If you are not aware of that, there is a complete video on that in this channel. I will link that in the description down below. You can watch that and hopefully you will be able to understand how to figure out the sum of all the ones in a given rectangle in just order one time with some pre-computation, right? So I'm not going into that, but assume that finding out the sum of ones in this rectangle is just order one operation. So in just order one time, you got what is the total sum. You can compare it with the total sum of ones in the complete grid. If they are equal, that's a valid candidate, otherwise that's not a valid candidate, right? So this is the current time complexity. We have to we can optimize this first of all. Why? Because if you just figure out if you take this route and extend it to figuring out two rectangles, it will simply be squared, right? And that is not sufficient because in the given problem you have to pick 3 distinct rectangles, and in that case it would be cubed, which will surely not fit in the time complexity. So we have to optimize this for sure. And what are the possible areas you can optimize? Notice that you are figuring out for each top left cell, you are iterating over all the bottom right cell. So let's try to remove this one. In other words, for each top left cell, I will figure out the optimal bottom right cell, and that operation I have to do it in less than order n cross m time to make the entire complexity smaller than what we have today, right? So think about it. We have to figure out the optimal bottom right cell and we have to cover all the ones, right? So this is the top left cell, right? So in other words, you don't care about what exists before it at all, right? So this is the current grid you care about. Now in this grid, you want to cover all the ones and you want to pick the smallest grid inside this grid which has all the ones. So the bottom right cell would be classified as R comma C, right? Some row and some column. Okay, so let's try to figure out R first. Forget about C, let's try to figure out R first. So what is the optimal row for the bottom right cell? So when you have to cover all the ones, right? So let's say you go from bottom to up. Now will this be the optimal row? The answer is no. Why? Because here there is no one at all. Now if there is no one at all, why you want to increase your area by one complete row? Doesn't make sense, right? So you will say, okay, this is not an optimal row for current top right cell at least. Let's move forward. Is this an optimal row? Answer is no, because there is no one at all in this row as well. So let's move forward. Is this an optimal row? Answer is yes, because there is a one in this row. So you can't skip this row at all. If you skip this row, it means you are skipping one as well, which is not which will make whatever candidate you will select, that will not be a correct candidate. So at this stage, what you can say is, okay, this is my optimal row for the bottom right cell. In other words, 2 is my optimal row for my bottom right cell. Now let's try to figure out C as well in the same fashion. Again, you want to figure out the optimal C or optimal column. So you'll start from the rightmost one and go to the left. Is this the optimal column? Answer will be yes. Why? Because there is a 1 here. Now if you skip this column, you will not be able to get this one in the current rectangle you are forming, and hence you need to get this row, this column as your optimal column as well. In other words, the optimal column would be 5. So if you combine these two, you will get the optimal cell or optimal bottom right cell for the current top left cell as well. And this entire operation which we have done to figure out 2 and 5, let's see if we can do it in less than order n time. If we are able to do this, then yeah, we have reduced our time complexity a little bit. So what we are doing, we are iterating over the first for the row, we are iterating over all the rows from bottom to top. For each row, I want to figure out how many ones are there in this particular area. And again, finding out number of ones in a sub rectangle is an order 1 operation, as we just mentioned. So this will be order 1 operation. If the count is 0, you will move forward. Again, figure out the sum of 1 in this area. Count is 0, move forward, and so on and so forth. So in a worst case, you will be iterating over all the n rows here, right? And in just order n time, you will be able to figure out what is the optimal value of R. In the same fashion for C as well, you are doing the exact same thing, figuring out, like iterating from right to left. For each cell, for each column, you are figuring out whether there is 1 or not in that cell, and that again you can do in order 1 time. So in order m time, you are able to figure out optimal C. So overall, in order n plus m time, you are able to figure out the optimal value of the right top of the bottom right cell, and this entire thing is optimized to n plus m multiplied by n cross m. Right? Now, can you optimize this further? The answer is yes. You can remove this as well. In other words, you can say I will figure out the optimal top left cell as well without iterating over all the top left cell. And how to do that? Exact same thing. You want to cover all the ones, right? So for the top left cell, you can start again, there is 2 things, right? R and C for top left cell as well. For R, you can iterate this time from top to down, because you want to take all the ones from the top. So you will start from top to down, exact same thing. For each row, you will figure out how many ones are there. If there are no ones, then you will move forward. If there are 1, you will stop. That's the optimal cell, right? So again, this entire thing will take you order n plus m time. So overall complexity is now simply order n plus m square, which is a lot better than what we had previously, right? So this is the overall time complexity of the current algorithm, and this is a lot better than the previous ones, right? So let's look at the pseudo code before we move forward. So the pseudo code will be very similar. We will simply figure out the top left and the bottom right cell. So for the top left, I will first start to figure out what is the value of R for the top left cell, and for that you will simply iterate over all the rows starting from 0, and for each row you want to figure out how many ones are there in that particular row. So for each row you will figure out how many ones are there in that particular row, right? And if it is greater than 0, you will break. In the same fashion, for down as well, you will figure out how many um, okay, it is not order n plus m square, actually it is 2 cross n plus m. However, you also have to do n cross m operation to make sure that this entire thing, this count operation, is order 1. So that, like, a small mistake on my side, but overall the complexity is order n cross m instead of n plus m whole square, right? So first figure out the top, then left, then down, and then right, in the same fashion. And this entire thing, all these 4 operations are just order 1 operation, assuming that there is some pre-computation done that will take us order n cross m time. So pre-computation is order n cross m, and then everything else is just order n plus m, right? So n cross m plus order n plus m is the overall time complexity, which is surely better than the previous ones, right? Now let's move forward and let's figure out how to solve the exact same problem for 2 rectangles. That is, given a grid of zeros and ones, figure out 2 rectangles that can cover all the grids, and obviously the sum of areas should be minimum possible, right? Now what is the brute force way to solve this? Again, one of the brute force way would be, okay, let's fix one rectangle. I will iterate over all possible first rectangle, right? So let's say you iterated over all possible first rectangle, and this is one possible first rectangle, right? Now once you have fixed the first rectangle, second rectangle can either be on the right or can be down, or it can be completely isolated, like somewhere in this part, right? It can't be the case that you have a rectangle that covers both the right side and the down side, because that rectangle, to cover anything from here and anything from here, you would need a rectangle that goes and overlaps with the original rectangle as well, right? So what that means is, if you have fixed a rectangle, you would need to figure out whether there is a one on the left side, on the right side, or on the down side, or on the left side or on the top side. Like for example, if you have taken a rectangle like this, then you would have 4 sides, right? There is a top side to it, there is a left side to it, there is a right side to it, and there is bottom side to it. So among all these 4, you can't cover or any of these 4, because if you want to cover at least 2 sides, you would need to intersect this rectangle as well, right? So in other words, once you have fixed the first rectangle, you will figure out how many sides of that rectangle will I need to take care of. If the number of ones in top, left, bottom, or right is greater than 1, then surely this rectangle is not the right choice. I have to make the switch. But you can think about it, this is becoming a bit harder, right? But if you carry forward this approach and assume that, okay, this is our first rectangle, let's not go about 4 sides for now, let's stick to 2 sides for now, and we will come to 4 sides later. So if you have this rectangle in the first place, you can either afford having ones on the right side or having ones on the down side. You can't afford both, right? So assume that there is no one. Let's assume this is 0. So assume that there is no one on the down side. So in that case, this entire thing is 0, right? And if this entire thing is 0 and you can't take any of these, so in other words, you have completed whatever you have to do for this entire piece. Now what you have left with is this entire rectangle, and what you want the minimum rectangle of this rectangle, which can cover all the ones in this area, right? And on the other side, if you, let's say, assume that there is no one on the right side, in other words, you have covered all these areas, all the ones in this area fully. Now you want to just cover all the ones in this area which is nothing but like there is an independent grid. You need to figure out the minimum area rectangle which can cover all the ones in this particular independent grid, right? So in other words, when you have two rectangles, when you want to select two rectangles and they should not be overlapping, those rectangles should either be on the top and down of each other or would be on the left and right of each other. They can't be both at the same time, right? So with that, can you split the responsibilities? Can you say, okay, let's assume that you have top and left, right? So let's assume that this is your partition. So in this case, what you want what is the maximum area, or what is the minimum area rectangle that can cover all the ones here? What is the minimum area rectangle that can cover all the ones here? And I will pick this rectangle and this rectangle, and that will be the minimum area of two rectangles that can cover all the ones in the entire grid, right? So that's just one partition. The same you can apply to the second partition as well. You can say, okay, I will get what is the minimum area rectangle that can cover all the ones here. What is the minimum area rectangle that can cover all the ones here? I will just sum them all up, and that will be my minimum area two rectangles that can cover all the ones in the entire grid. Again, we are able to do this because we know that if we want to have two non-overlapping rectangles, they can either be left and right or on the bottom and down of each other, right? They can't cross anyway. So we can try out every possible rectangle or every possible partition. For each partition, we will answer the same question, that give me a rectangle in this area that can cover all the ones. Give me a minimum possible area rectangle in this area that can cover all the ones. I will sum them all up, and that will be the minimum area of two rectangles that can cover all the ones here. Now that's about the vertical partitioning. You can simply do the same thing for horizontal partitioning as well. In other words, you can say what is the minimum area of the rectangle in this, what is the minimum rectangle that can cover all the ones in this area. Similarly, what is the minimum area rectangle that can cover all the ones in this area? Sum them all up, and that will be the minimum possible area of the rectangle that can cover all the ones in the complete grid, given this is the partition. So you can try out all possible horizontal and vertical partitioning, and for each of the partition you can ask the exact same question to figure out the two rectangles which you are in search for. So in other words, this is how your different partitioning will look like. You will first try out, let's say, all the horizontal partitioning, and then you will try out all the vertical partitioning as well. For each of them, what you need, you will simply ask, okay, give me the minimum possible area that can cover all the ones here. So let's assume that that function is named cover. So that cover function is nothing but what you have done here, right? So here you have said that, okay, what is the minimum area of the rectangle that can cover all the ones in the grid, right? And that's the exact same thing you want here. What is the minimum area of the rectangle that can cover all the ones in this grid, right? You can apply the exact same algorithm that you have applied there. So in other words, in just order n cross m time, you will be able to figure out what is the minimum area of the rectangle that can cover all the ones here. Similarly, in just order n cross m time, you will be able to figure out what is the minimum area of the rectangle that can cover all the ones here. So in just order n cross m time, you will be able to figure out what are the two rectangles that can cover all the ones in this grid, given this is the horizontal partitioning line. Similarly, in order n cross m time, you will be able to figure out what is the minimum area of the two rectangles that can cover all the ones in the given grid, given this is the horizontal partitioning line. In the same fashion, this will also take order n plus m time, and finally this will also take order n plus m time, right? Now overall, you are doing order n cross m operation n number of times, which is basically number of rows, right? In the same fashion, here as well you will be asking the same question: what is the minimum area of the rectangle that can cover all the ones in this area? Minimum area of the rectangle can cover all the ones in this area. So again, this you can figure out in just order n cross m time. and similarly this will also be order n cross m, and so on and so forth, right? So the complexity would simply be order n cross m multiplied by n plus m. So in this time you will able to figure out what are the two rectangles, what is the minimum possible area of the two rectangles, and cover all the ones here. Again, just to reiterate one last time, we are able to do this because we had observed that once you have fixed one rectangle, the second rectangle can't overlap, which in turn means you can't have two sides, like you can't have a rectangle that can cover two sides. In other words, you can't have ones on the two side. And if you are saying that you can't have one on the two sides, then you would need to, like, in other words, you're saying that you can have one full left half or the top half filled, like all the remaining things in the left half or the top half filled with 0, which in turn means everything. You can just ask what is the minimum area of the rectangle that can cover all the ones in this entire top half or in the entire left half, right? So hope this entire thing is clear. Now let's quickly look at the pseudo code before we jump on to solve the original problem, which is figuring out the number of minimum area with three rectangles. So for now, this is the pseudo code for the two rectangles. What we are doing is simply what we shown here. We will try out all possible horizontal partitioning. We will try out all possible vertical partitioning. For each horizontal partitioning, we will figure out what is the top minimum area of the top side, what is the minimum area of the downside, right? And we will simply sum them up to get the minimum area of the two rectangles that can cover the entire one in the complete grid, right? So in the top main area, what you're doing, you're simply calling the cover function, which simply is the how many, like what is the minimum area to cover all the ones in a grid, and the grid is simply starting at 0, 0 and ending at r columns, which basically means this particular bottom right cell, right? So this is the top left cell, this is the bottom right cell. So in this grid, figure out what is the minimum area of the rectangle that can cover every ones. Similarly, this is the top left cell and this is now the bottom right cell. You have to figure out what is the minimum area that can cover all the ones in this area. So this starts at r plus 1, 0 and ends at last row and the last column, right? So in the same fashion, for vertical partitioning, you will have all possible vertical partitioning. You will figure out what is the minimum area from the left side, what is the minimum area from the right side, sum them all up to get the minimum area of the two rectangles that can cover all the ones, right? And for the left side, you will start, your top left cell would be 0, 0 always. The bottom right cell of the left half would be last row and the column where you are partitioning. So last row and the column where you are partitioning. And the next would be 0, c plus 1 and row minus 1, columns would be the last one, which is basically the bottom right cell of the complete grid. So you will keep taking minimum across all these possible partitioning, and finally answer will contain the minimum area possible. So hope this entire solution is clear. Now if it is not clear, I would strongly encourage you to rewind and watch the previous section again, because the solution with three rectangles will be building on top of that. So now comes the original problem, which is we have to select three rectangles with the minimum area that can cover all the ones, right? So again, so what's the brute force way to solve this? You have to pick three rectangles, right? Now you can say, okay, I will fix first rectangle, right? And once you have fixed the first rectangle, you have to pick two more rectangles. Now again, those two rectangles can't be overlapping. So either one of the rectangles will be on the top, one of the rectangles will be on the right, or it could be on the left, or it could be on the down, right? They can't be both. So in other words, what you're saying is you can afford one only on two sides. If you have one on more than two sides, no matter what you do, you will not be able to cover the remaining ones with just two rectangles. So in this particular example, if you see, you have one here, you have one here, and you have one here as well. Because you have one on three sides of the line, three sides of the cylinder rectangle, you can't cover all these three ones with just two rectangles. We need at least three rectangles for that. And you can like this, in this particular scenario, this cylinder rectangle is not a valid cylinder rectangle. You can try out other possible first rectangle, right? So let's think about this in a very generic fashion. So let's not look at the four sides, but rather let's just look at the two sides only, right? So for now, let's say this is the first rectangle that you have selected. So in this case, you have two choices. Like you have to select two rectangles. So one rectangle could be on the left side and one rectangle could be on the down side, right? Or in other words, one rectangle could be on the right side or one rectangle could be on the down side. Notice that these two rectangles can also not overlap, right? So in other words, this part, whichever is remaining, should either be a part of the rectangle that comes here or would be a part of the rectangle that comes here, right? It can't be part of the both the rectangles, right? So if you think about it closely, this is exactly what we have done before, right? In other words, what we are saying is, if we have a partition here, or rather we could have a partition here or we could have a partition here, but one of these two partition we should have. So if you just try to simplify this, we know that this part can either goes with this or it can go with this, right? In case it goes with this entire thing will be one complete piece and this entire thing will be one complete piece. In case this goes with this entire thing will be part of like one rectangle which you will form out of it, and this entire thing will be part of another rectangle. In other words, one observation here is there is always a line which you can draw, either horizontal or vertical, such that two rectangles are on the one side of it and one rectangle is on the other side of it. So in this particular example, if you draw this line, you know that these two rectangles are on one side of the line and this rectangle is on the other side of the line. In similar fashion, you can, if you want this to be a part of this rectangle, you can draw it as a vertical as a horizontal line, and this will be part of one rectangle and this entire thing will be part of one rectangle, right? So you can always draw a line and two rectangles will be on top of it and one rectangle will be on the bottom of it, or if it is a vertical line, two rectangle will be on the left of it or one rectangle will be on the right of it. Note that this can go either ways, that if you have a horizontal line, you can say that there are two rectangles which is on the down and there is just one rectangle which is on the top. Possible, right? So if you think about it, we can model this entire thing in the exact same fashion. That is, we just want to iterate over all possible valid partition. Now for each partition, what we want, okay, give me the minimum area that can cover this entire thing with two rectangles. Give me the minimum area that can cover this entire thing with one rectangle, or vice versa, right? In the similar fashion, if you have a vertical partitioning, let's say this, you are saying give me the minimum area that can cover this entire thing with two rectangles. Give me the minimum area of the one rectangle that can cover this entire thing, or vice versa, that is, give me the minimum area of one rectangle that can cover this entire thing. Give me the minimum area of two rectangles that can cover this entire thing. You can try this out for all possible horizontal and vertical partitioning and you will be done. In other words, we can simply try out all possible horizontal and vertical partitioning and we can say, okay, give me the minimum area of the two rectangles that can cover all the ones here, minimum area of one rectangle that can cover all the ones in this, minimum area of two rectangles that can cover all the ones here, minimum area of one rectangle that can cover all the ones here. Similarly, minimum area of two rectangles that can cover all the ones here, minimum area of one rectangle that can cover all the ones here. And finally, minimum area for two rectangles to cover all the ones, and minimum area of one rectangle to cover all the ones. Now you might be wondering, okay, that's good, but what if I have this line and I have two rectangle on this side and one rectangle on this side, right? So you have to try out that as well. That is one possible one possibility as well. In other words, you will say, what is the minimum area to cover everything here in one rectangle? What is the minimum area to cover everything here in two rectangle? In the same fashion, you will ask for the same thing from every other partitioning as well. Minimum area to cover everything here in one rectangle, minimum area to cover everything here in two rectangles. Finally, for others as well. So the one you have done for horizontal partitioning, you will do the same thing for vertical partitioning as well. What is the minimum area to cover everything here in two rectangles, minimum area to cover everything here in one rectangle. And in the same fashion, you will have the counterpart as well, which basically is what is the minimum area to cover this entire thing in just one rectangle, minimum area to cover this entire thing in two rectangles, and so on and so forth. So for each vertical partitioning, you will try out two possibilities: the left side with two rectangle, right side with one rectangle, or left side with one rectangle and right side with two rectangle. And for finding out the left side with two rectangle, you can use the algorithm that we have for two rectangles, right? This particular algorithm. Let's say this function is f2, and for one rectangle the function is f1. So you give a grid in f2, it will give you the minimum area to cover the entire thing with two rectangle. You give a grid in f1 and then will give you the minimum area to cover the entire thing with just one rectangle. So you can call f2 here for this grid and f1 here, or f1 here and f2 here, and keep taking on minimum across all these different partitions, and finally the minimum you got will be your answer, right? So this solution is again built on top of the previous solution itself, which basically we are basically saying that because we know that there will be one partition where two rectangles will be on the one side and one rectangle will be on the other side fully, we are able to apply this. So I hope this entire thing is clear. I am not showing you pseudo code for this three rectangle because that would be exactly similar to what we had for two rectangles, just there are two cases instead of just one. So would encourage you to pause and try to code this entire thing by yourself. You can literally write three functions, one for f1, one for f2, and for f3 as well. And in f2 you can call f1s, in f3 you can call f2 and f1, right? So next, let's look at the time complexity of the entire thing. So what you are doing, figuring out how many, what is the minimum area to cover this entire thing with two rectangles would take you order n cross m multiplied by n plus m time, right? That's the complexity of the f2, and minimum time to cover this entire thing with one rectangle would simply be n cross m, right? So overall complexity would simply be n cross m multiplied by n plus m plus 1. So let's forget about plus 1 for now. So this is the overall complexity for just one rectangle. So for just one possible horizontal partitioning. Similarly, you have n different horizontal partitioning, so this will be repeated n number of times, right? In the same fashion, you will have this entire thing repeated again with just the order reversed, so this will be multiplied by 2, right? Now this entire thing is for the horizontal partitioning. For vertical partitioning, again, figuring out what is the minimum area of the two rectangles that will cover a grid would be n cross m multiplied by n plus m, right? And minimum area to cover this entire thing with just one grid would simply be n cross m. So again, the complexity would simply be this multiplied by m number of times, or rather 2m number of times. So this entire thing, let's just get rid of this, and if you do this, it will be 2m, right? And if you just take this entire thing common and remove 2, this will be order n plus n cross m multiplied by n plus m whole square. And this is sufficient to pass the given time constraint because n is up to 30 only. So 30 cross 30 multiplied by 60 square, which is fine. So hope this entire solution is clear. I would strongly encourage you to pause and try to code this entire thing by yourself, because that is the point where you understand what you don't understand. So let's move forward. The code is exactly what we just discussed. We just called min3 rectangle with the top left and the bottom right cell. Now in the min3 rectangle, we will try out every possible horizontal and vertical partitioning. For each partitioning, we will figure out two different things. One, for the left, let's say we are trying out vertical partitioning. So for the left side, if we cover the left side with just one rectangle, if we cover the left side with two rectangles, right? Similarly, if we cover the left side with two rectangles and right side with one rectangle, and we will simply take the minimum across those two, right? So this is just one difference, like min rectangle is not giving you the area, rather it is giving you the exact rectangle which is minimum. So let's not worry about that, we just care about area. So we just call the area function on this rectangle, and this will give you the area of this rectangle. So this entire thing will work, like we are trying out all this thing for the vertical partitioning. We'll do the same thing for horizontal partitioning as well, as in for any horizontal partitioning, we will figure out what is the minimum area of two rectangle from the top side, minimum area of the one rectangle from the bottom side, or vice versa. So minimum area from, this should not be left or right, it should be top or down. I just copy pasted. So what is the minimum area to cover the top side, minimum area to cover the down side with two rectangles, minimum area to cover the top side with two rectangles, and the down side with one rectangle. And we'll simply take the sum of these two and take minimum across all of them. Now min to rectangle is also similar. We are simply trying out all possible vertical and horizontal partitioning, and for each of them we are figuring out what is the minimum area to fill the right and the left, or top and the down, right? And finally, for minimum area for this entire rectangle, we are figuring out the left of the top left cell, the right of the bottom right cell, the top of the top left cell, and the bottom of the bottom right cell. And if there is no one at all in the current grid, we have to return a rectangle with area 1 at least. So we just selected any rectangle with just area 1, right? Because it is given that you should have all the rectangles with non-zero areas. So we just selected a rectangle with any 0 in it. Otherwise, we just return the top left and the bottom right cell. And the area function is very simple. We simply take the length and the breadth and multiply them to get the area of the rectangle, right? So hope this entire solution is clear. I will share the code in the description below. You can check it out if you still face any issues. If you have any doubts in any of the piece, feel free to follow up in the comment section below. I would be happy to answer. And I hope you learned something new from this video. I will see you in the next